Greetings, gentle readers, fellow earthlings. Today, March 11th, 2026, in Reading Foundations, this series of podcasts, video essays from a study with Ross Finlayson and myself, here will be more about reading and foundations and the new box of books, which has just arrived as I gathered it some years ago. Over on the side is kind of a stack is about kinematics and the ideas of mechanical engineering mostly, about what goes into mechanisms with regards to usual accounts of energy and advantage, what then make for economy, and these usual ideas of the employment of informational advantage, and then as for briefly computational advantage, for mechanical advantage. Then the kinematics gets into the field is mostly about the rotational and the moment arm of things that have to do with the accumulation of energy as for power doing work, and then that they make for devices, for example, as of the clock ticking in the background, and the automobile, or the lever, the shovel, anything with a handle is basically as an account of the application for kinesthesiology in kinematics, or the human body's application of mechanics. That's just kind of the side stack over here that's been collected, and includes stuff like Lamb's Hydrodynamics, and I've been reading again the Electron theory of matter of O.W. Richardson, from about 1916, which is an account of electron physics as arrives after Geiger and Rutherford, and then for Wilson, H.A. Wilson, and then C.T.R. Wilson, separate people. And then for Millikan, and Millikan, the account after Jeans and Rayleigh Jeans for spectroscopy, and then from Faraday, Coulomb, Ampere, the laws make for Ohm and Kirchhoff the laws of electrical devices and electricity, the theory, the electron theory of matter. And about its account is what I was reading and looking is about is the three constants C defined. And people will be familiar with light speed as C, the constant, and the L principle of Einstein's relativity theory. That Richardson gives a great account as for the time and enduring today, as of this time, of the electron theory of matter and electron physics. He states plainly that is about an ether theory, and then similarly about some charge ratios to arrive at one constant C, and then another one is about light speed, and then another one is about the electrodynamics. It's rather fulfilling to see that under this E Einstein E energy equivalency, there are all these F Lorentzians then for Henrik Anton Lorentz, and the idea that it's got a Laplacian plus a minus another Laplacian of the space-time, and then the metric on the other side. There are many ways that these F for fields and forces, F Lorentzians, can then make for, in many accounts, helping to show why when the equivalency is kind of a classical balance of things, that it's as well, according to deconstructive accounts, all these many things that make it in the more potentialistic theory, the more real, thorough, and holistic account of the theory, that's to be discovered and rediscovered, these kinds of things. So getting into the box of books, see here on the top of the box is On Knots by Kauffman. On knots, K-N-O-T-S, knots, tying of the knots, the tension of the knots, the how one might say, the character of knots, and by Louis H. Kauffman, Kauffman. Annals of Mathematics Studies, Princeton University Press. It's about $15. Annals of Mathematics Studies, number 115, 1987. Cloth-bound editions of Princeton University Press books are printed on acid-free paper, and binding materials are chosen for strength and durability. Paperbacks, while satisfactory for personal collections, are not usually suitable for library rebinding. So, glued, this book would be vis-a-vis stitched. To the memory of Andres Reyes. The contents and the chapter descriptions are as for an introduction, linking numbers and Reidemeister moves, the Conway polynomial, examples in skein theory, S-K-A-I-N, the skein, web, net, weave, detecting slices and ribbons, a first pass. Then chapter 6 is miscellany, and so then these sections in miscellany are quaternions and belt trick. That we would find we might be able to speak back to the account from the Penrose's Road talk about Penrose describing spin and the quantum spin is about this. 2, rope trick. 3, topological script. 4, calculi. 5, infinite forms. 6, quandles, not a word regularly heard of before. Quandles, Q-A-N-D-L-S, quandles. 7, topology of DNA. Deoxyribonucleic nuclear acid, or nucleic acid, of course, is well known as forming the chromosomes in the cellular machinery of the carbon-based life forms that we are. Knots are decorated Fibonacci trees, describing a model of knots in a few pages. Alhambra mosaic. So the Alhambra is it's in Spain, I believe, and if I make a mistake about something so general as that, it's not so relevant. But it would speak to the geometric forms and the ideas of tessellations and as the like of M.C. Escher and the drawings and reflections and symmetries that fill or pack or tile the plane, the mosaical. Odd knot. Pillars family tree. P-I-L-A-R. Pillars family tree. The untwisted double of the figure 8 knot. Applied script, a ribbon surface. Kirchhoff's matrix tree theorem. States and trails. The map theorem. The Mobius band. Here there was discussed at some point in time and several times with regards to these notions of the Mobius strip and the Klein bottle. The ideas about the turns and the twists and what that makes for geometry and then for torsion and the torsional setting, what makes the accounts in the unlinear is kind of how that's associated. The Mobius band is that section 17 of chapter 6. The generalized polynomial and irregular isotopy in twisted bands. Then chapter 7 is spanning surfaces and Seifert pairing, ribbons and slices then, Alexander polynomial and branched coverings, Alexander polynomial and ARF invariant, free differential calculus. Chapter 12, cyclic branched coverings, or cyclic branched coverings, signature theorems, theorems is with regards to the signatures of knots, G-signature theorem for 4 manifolds, signature of cyclic branched coverings, an invariant for coverings, slice knots, calculating sigma sub r for generalized stevedores knots. Stevedore, that would probably be not a proper name. It refers to the stevedore is S-T-E-V-E-D-O-R-E is generally one who makes handling the livestock is, I think, the usual idea, or is of a longshoreman or something like that. Singularities, knots, and Brieskorn varieties, B-R-I-E-S-K-O-R-N, Brieskorn varieties. The appendix is generalized polynomials and a states model for the Jones polynomial, and then knot tables in the L polynomial. These notes on the theory of knots comprise an expanded version of a seminar held in the Departamento de Geometría y Topología at the Universidad de Zaragoza, Spain, during the winter of 1984. Due to the supernatural enthusiasm and persistence of the members of the seminar, thus this author was given the energy to record a, we believe, careful set of notes and to relish the process. The notes began with the most elementary concepts of diagram moves and linking numbers. Then they moved quickly, perhaps steeply, using minimal technical apparatus to problems of knot cobordism and the ARF invariant. So when thinking of knots, there's basically as for loops and then passing through the loops. And then there's tying knots and then untying knots. It's often simpler to approach untying a knot than to tying a knot. Yet tying a knot has approach to it basically the bights and the loops and the twists and then over and under and about and around and these kinds of things. And so I first started to learn tying knots after any person's usual experience with tying their shoes. And I suppose it was in the youth organizations where they're provided merit badges for learning how to tie a variety of knots. And then at some point in time, I found in a maps store a cool little pocket guide laminated for tying various kinds of knots. And then and I could basically make a quick slip knot, and I at one point in time knew how to make a half hitch and a full hitch compared to like a square knot or granny knot, the shoelace knot, the surgeon's knot, often used for tying fly or fishing gear, and these kinds of things is not unfamiliar knot. Mostly though, all I know is a square knot, a granny knot, because all I can really do is make a twist and just keep piling twists on top of that. Then vis-a-vis making loops in the shoelace knot, vis-a-vis the square knot. And then it's to be discovered though. Many things to do with knots, and then the application of knots, and then also the application of a tool as like the marlin spike. Or otherwise a screwdriver or something like that, with regards to that providing a lever and mechanical advantage for the tying and untying of knots, and then the tying and untying of knots is quite a thing. Then sometimes it's said is that knots are a particular feature of 3 dimensions, or where the cross product exists, like 3 or 7 dimensions, or that knots don't exist in 4 dimensions, as it's kind of said. And so that's kind of the idea is like, well, yeah, if you can pull on free ends that you can make, it would come loose any kind of tangle in 4 dimensions. And I'm not to be exactly so that's so if there's cases where something it holds itself in the planar and so basically keeps itself the tension in 3 dimensions, say. These are kinds of aspects of the trivia that get associated with fields of descriptive accounts of dynamical systems, is what they may be, with regards to knots and the character of ropes or twine or cordage, the usual accounts of materials, and then also for stitching and sewing and the knots associated with otherwise the weave and web, warp and weft of cloth and these sorts of accounts. This is another key exercise providing an entry point into a classical paper by Durham and to the work of Riley on hyperbolic structures on knot complements via representations of knot groups. We only indicate a direction here. Nevertheless, this exercise is the link between these notes and Riley's work and the spectacular results of Thurston and his school. Crossings, knots. Page 206 is the square knot and the granny knot. So like for graphs, then knots would have a theory and a descriptive account. There are many aspects of knots that could be related to graphs, and then there are also many aspects of knots as would be related to curves. Torus knots, the trefoil, clasp, that the usual square knot or granny knot starts with clasps, if that's what they'll be called then, instead of twists. So this is a kind of an account of developments in a theory of knots, and then getting into the hypergeometric, or rather the hypercomplex numbers, the pure quaternions, and it's about rotations and reflections, and then about the symmetries and groups. Thus, Milnor's theorem is that the links of isolated singularities are fibered knots. And Milnor's, Milnors. And so for torsions vis-a-vis knots, there's generally the usual idea is there aren't any knots in the eddies and ripples and whirls and vortices of turbulence in current and flow, because it's a continuum mechanics and for least action and these sorts of accounts. Yeah, it could still be modeled as those in terms of the definition of say constructive interference or resonance circuits that make for then otherwise models of the adiabatic flow. Why that it would still be a thing. Monodromy, it mentions monodromy, that's always a great thing. The structure of the vibration phi about s to the 2n minus 1 minus n sigma as goes to s1 is given by the monodromy, h of f to f, where f is the fiber. It is easy to see from our discussion that this monodromy consists in multiplying each coordinate by the corresponding root of unity in this case. So he's built up for the attachment to the complex numbers and this kind of thing about the monodromy, because the monodromy is basically for the holonomic and the holonomy and the monodromy, that the monodromy after cobordisms and these kinds of accounts is that it does flow and that the formation and dissipation is for the oscillative and restitutive and the attenuative and dissipative in the theory of knots. And then making here, for example, examples of diagram algebra relations. When the algebra is just a way to talk about what the diagram gives, but they both have to hold together to be so. And then he gives a bunch of knots, the knot tables, much like graph tables, up to isomorphism as it may be, or equality as it would be so. And then a great bibliography. Quasicrystals and Geometry by Marjorie Senechal. Marjorie, Marjorie Senechal, Seneschal. Quasicrystals or quasicrystals in geometry. Quasicrystals in Geometry brings together for the first time the many strands of contemporary research in quasicrystal geometry and weaves them into a coherent whole. The author describes the historical and scientific context of this work and carefully explains what has been proved and what is conjectured. This, together with a bibliography of over 250 references, provides a solid background for further study. The discovery in 1984 of crystals with forbidden symmetry posed fascinating and challenging problems in many fields of mathematics as well as in the solid-state sciences. By demonstrating that order need not be synonymous with periodicity, it raised the question of what we mean by order and how orderliness in geometric structure is reflected in measures of order such as diffraction spectra. Increasingly, mathematicians and physicists are becoming intrigued by the quasicrystal phenomenon, and the result has been an exponential growth in the literature on the geometry of diffraction patterns, the behavior of the Fibonacci and other non-periodic sequences, and the fascinating properties of the Penrose tilings and their many relatives. So here that would kind of get related generally to normid rings, because for a ring to have a norm when it's bounded or compact, then it gets into various notions of the projections and the geometry. For the Escherian is usually graphically given in enrichment. Then those being quasi-crystals about symmetries, and the notions that the crystalline basically reflects on the lattice, and the fact that there are particular resonances that would that would take the angles that would like go out through the corners or grow out through the faces, the edges and the faces of the packings that make for what is the crystalline, then for Schoenflies and Christoffel, the usual accounts of the crystallographic, this quasi-crystallographic. This first ever detailed account, I imagine the author might intend, of quasi-crystal geometry will be of great value to mathematicians at all levels with an interest in quasi-crystals and geometry. It will also be of interest to graduate students and researchers in solid-state physics, crystallography, and materials science. And I observe that they don't observe the standard serial Oxford, Harvard comma when grouping and listing and enumerating a list of terms. I always use the standard comma, and it's called standard for a reason, because it reflects not just a separation of terms from being compound words, but that also it's a pause, naturally enough, in the speech when enumerating lists of an item. I'm very against this Cambridge comma, or what you might call it, the omission thereof. And it's never good, and it's just not worth it to save the space of a comma. That said, I'll leave that to matters of style. I don't have anything against it. Aperiodic Penrose alpha. There's an illustration. So it looks kind of like a Klein bottle by the noted sculptor mathematician Helaman Ferguson, was commissioned by Marjorie Senechal, who worked closely with him on its design. Completed in 1995, it stands in the lobby of the Clark Science Center at Smith College. The sculpture of carnelian granite rests on a base of black granite Penrose tiles. The articulated torus encodes the composition matrix of the tiling. Quasicrystals in Geometry by Marjorie Senechal. Louise Wolfe Kahn, Professor of Mathematics, Smith College, Northampton, Massachusetts, by the Cambridge University Press. So, Cambridge. First published 1995. First paperback edition with corrections 1996. And then the contents of the chapters are Pasta's prologue, lattices, Voronoi cells, and quasicrystals. So the Voronoi cells are kind of like elementary crystals. Introduction to diffraction geometry. And about what crystallography intends to entail often enough is for diffraction gratings and describing by the critical values what makes for the behaviors of otherwise these milieu as media. Order on the line, tiles and tilings, Penrose tilings of the plane, the aperiodic zoo. A zoo is usually just used to describe a bunch of the exotic. An atlas of tiling transforms, and then an atlas is both a map and then what holds it up, usually. So, giving accounts of delay, for example, and what reflection and the incident then makes for refraction and diffraction, talking about the translation of the aperture, the grading, the account of the aperture orifice, affects a phase shift in the amplitude, making for accounts of Bernoulli and Venturi. The infinite strings, and so infinitary analysis. Prototiles. We will show that the Voronoi cell of any vertex is completely determined by its star. In his remarkable paper, De Bruyne also showed that every Penrose tiling is either the dual of a regular pentagrid that satisfies the sum condition, or else it can be uniquely associated to the dual of a singular pentagrid. The pentagrid construction reveals the reason why locally legal configurations may not be globally legal. The pentagrid is a blueprint for the Penrose tiling. It completely determines the relative positions of the tiles. Each line of each grid intersects all of the lines of the other grids. When we create a patch of tiles, we're specifying the positions of several lines of several grids, thus implicitly the positions of possibly distant intersection points. the same time, we are also specifying the position of tiles that are not necessarily adjacent to the original tile configuration. So the pentagon or pentagrid here is about things like Pappus's theorems and the 9-line theorem or the 9-circle theorem or the 3-line or the 3-circle theorems. Then are as about accounts of phi and usual accounts of the existence of root 5 in descriptions of matters of phi and other solutions of x squared plus minus x plus minus 1 equals 0, their roots, that could be related then. Prisms is a rhomboid or rhombic and not exactly rectangular or square. Amon tilings, those show up first, the Amon tilings. So a great account of tilings and tessellations is so arrive at it. And what that means when there's the affine, meaning it's preserving translation, rotation, skew, and shear or not, and then for matters of metric and norm, and the normid rings and these kinds of things make for why Penrose needs those to say things. Some code, eigensystems, group actions, a mathematical tool bag is the sort of appendix. Weil and Cassels, the structure of orbits of Z modules, subgroups. A generalized function is a trace. The map is a generalized function. Parseval formula, Parseval, then for Plancherel. The Wiener diagram. The Wiener diagram is valid for densities of finite Delaunay sets, D-E-L-O-N-E sets, but not for Dirac combs or Dirac combs. Johnson showed that the Dirac delta is an element of C, since C is a linear space, so are all finite sums of the deltas. Explaining why there's some particulars in singular elements and otherwise what are considered usual milieu. This is a book by Michio Kaku, Quantum Field Theory, A Modern Introduction. So Kaku is a popularizer of physics in the popular press. And he's familiar with notions of things like string theory. So in Quantum Field Theory, A Modern Introduction, this is more of a textbook and a tour de force of just showing that he has an outline of the usual formalisms. Talking about the Lagrangian, instantons and anti-instantons. So also some of the super-classical accounts and the extensions, since in any singularity, as of a singularity theory, that is only a branch in a multiplicity theory, and vice versa. Talking about the quantum mechanical, talking about tunneling and scattering, thusly. WKB methods. Solitons is this chapter. Talk about Baecklund, so Bianchi and Baecklund, as for Ricci and Regge, R-I-C-C-I and R-E-G-G-E is about Bianchi and Baecklund. Usual formalisms of the quantum mechanical and the relativistic together. And for the Ricci tensor, that being about solving things like the torsional again as well. Or these sorts of accounts. Simulations. Particle confinement. One of the main reasons for introducing lattice gauge theory is to calculate effects that lie beyond the reach of perturbation theory, such as the confinement of quarks. Although quark confinement has not been rigorously proved within the framework of QCD, we provide compelling reasons for believing that quarks are confined in lattice gauge theory. In general, if the potential between two quarks is proportional to the distance between them, then the two quarks can never be separated. Confinement equal is V of R, or the potential is on the order of sigma R, where sigma is called the string tension. If we try to separate the quarks by force, then the restoring force of the linear potential between them grows sufficiently rapidly to prevent them from being separated. This is the gluons. But it only kind of comes into effect as the restoring force. So to say they're confined is more so to say they're constrained, because by asymptotic freedom is on either side of that. So they are yet as well. That I guess that's all the particle confinement is about the gluons. Furthermore, the string may break, so that's when they're not confined. So. Quark anti-quark pairs. Thus, they can never be separated if they are bound by a linear potential. That's just kind of the classical account and why the superclassical account gets into that. But this is stating that even after something like asymptotic freedom, this is added to the theory after the quantum chromodynamics to explain why it doesn't fall apart. We will now see that in the strong coupling limit, the lattice gauge theory confines quarks. Sets up the Wilson loop, which is a surface integral, or a contour integral, is about the trace of some coefficients in the tensor terms, tensor coefficients. All that up in Euler's identity as the rotation, where C represents a closed loop and where P represents the path ordering of the exponential along the loop. This means, parenthetically, that we cannot simply perform the line integral dx mu of the tensor coefficients along the loop. We must first split up the line integral into an infinite number of infinitesimally small exponentials, take the product of them ordered sequentially along the loop. So that's as about relating that to the classical part, usually, of the path integral. Notice that the Wilson loop is gauge invariant. Well, it doesn't really say that it really doesn't say that it's not. It's the idea, but it depends on that it is, in a sense. To be invariant, meaning it's got no other interacting terms otherwise. So saying that is so is then to give as like a criterion and a condition he needs. So it's kind of like saying is like, this is a definition in the theory and it holds. Otherwise, it's not in the theory. But mathematics has all its own theory. Talking about the Stanford Linear Accelerator. In summary, the slack deep inelastic scattering experiments demonstrated the importance of Bjorken scaling. Bjorken, Bjorken scaling. Ultimately, the scaling experiments were explained in terms of gauge theory and the renormalization group. So renormalization in quantum mechanics is after denormalization. Quantization is denormalization. So as saying, so that's kind of like, as again reflecting on the normid rings about metric and norm, because that's what gives the algebraization of these things. And then gauge theory is a great account of after field theory, because for a long time it's like, well, physics, according to all our experiments, it's a field theory, and that just reflects on the continuity of things mostly. And because before it was just forces, but then forces let out and don't compute up all the potentials. Fields, and then a gauge theory is just a field theory. Then with regards to what the gauge is, it's just like, well, it's the curvature, and so it's for all this torsional stuff and anything to do with metric and norm and the unlinear, that's what it is. So yeah, physics is a gauge theory all this time. And then that the real gauge is or R gauge. That's the question of gauge theory, is what is the R, the letter R, what is the R gauge? Here it says of a spiral space-filling curve, which also affects to reflect the cosmological constant in its placement, a symbolic operator. Natuurlijk, werkelijk. Simply. The Cabibbo suppressed transitions. So this gets into tensors and these kinds of. This is a great book, and it's really talking about lots of different things. Does quantum field theory really exist? Forests and skeletons. Dimensional regularization of gauge theory. Counterterms in gauge theory. BPHZ renormalization of gauge theories. Anomalies. Mixing angle and decay processes. The Cabibbo angle. CABIBBO. The standard model. The standard model of Higgs quark hadron physics. Not the old standard model, and not necessarily the new one. Coleman Weinberg, Nambu Goldstone. Integration over Grassmannian variables, Grassmann variables. Probabilities of quantum mechanics, the photon propagator. Schwinger-Dyson, Ward-Takahashi. Yang and Mills, Ward-Takahashi. Kluser-Klein. Lamb and Rutherford, I must imagine he meant Rutherford, but Rutherford. Lamb and Rutherford. The original Dirac electron in a classical Coulomb potential, as we saw earlier in section 4.2, predicted that the energy levels of the hydrogen atoms should depend only on the principal quantum numbers n and the total spin j. So these two levels should be degenerate, meaning that they can't be degenerated anymore. The calculation of the Lamb shift is rather intricate. So Lamb and then Lamb is in effects here. Calculation of the Lamb shift is rather intricate because we're dealing with the hydrogen atom as a bound state problem, and also because we must sum over all radiative corrections to the electron interacting with the Coulomb potential that modify the naive mu bar gamma naught u mu a to the naught vertex. So as of a kind of an adjoint setting, and about the group theoretic operations that make for that then into the Hermitian, it cancels out, and then by Fourier coefficient. These corrections include the vertex correction, the anomalous magnetic moment, the self-energy of the electron, the vacuum polarization graph, and even infrared divergences. The original non-relativistic bound state calculation of Bethe, which ignored many of these subtle higher order corrections, could account for about 1,000 megahertz of the Lamb shift, but only a fully relativistic quantum treatment could calculate the rest of the difference. So this helps go to show that the mathematics and the physics is a lot more thorough what's going on here. So let's see if in the introduction that we can find something about it. Kaku dedicates this book to his parents. Copyright 1993. He says, in the 60s, there were a number of classic books written on quantum field theory. Because of the phenomenal experimental success of quantum electrodynamics, QED, quantum field theory became a rigorous body of physical knowledge, as established as non-relativistic quantum mechanics. In the 1970s and 80s, because of the growing success of gauge theories, it was clear that a typical one-year course in quantum field theory was rapidly becoming obsolete. A number of advanced books appeared on various aspects of the gauge series, so often a one-year course in quantum field theory became disjoint, with one book on QED being the basis of the first semester and one of several books on various aspects of gauge theories being the basis of the second semester. Today, because of the success of the standard model, it is necessary to consolidate and expand the typical one-year quantum field theory course. There's obviously a need for a book for the 1990s, one that presents this material in a coherent fashion, uses the standard model as its foundation in the same way that early books used QED as their foundation. Because the standard model is rapidly becoming established as QED, there is a need for a textbook whose focus is the standard model, with the Higgsy. Because the experiments necessary to go beyond the standard model are rapidly becoming prohibitively expensive and time-consuming, we're also aware that the development of physics in the next decade may become increasingly theoretical, and therefore we feel that an attempt should be made to explore the various theories that take us beyond the standard model. It's much similar in O.W. Richardson's account of the electron theory of matter, because after the first 6 or 7 chapters, or the first about third of the book and half the book, then all the rest of it is like, and that this is all the other stuff that science knows by its data is in effect. So figure it out. By taking this intermediate approach, we hope to provide the student with a firm foundation in many of the current areas of research without overwhelming the student in an avalanche of facts. We will consider the book a success if we've been able to avoid these extremes. So something like this is really great and speaks very well to my image of that researcher as a physicist. Geometric Theory of Diffraction, edited by Robert C. Hansen, IEEE Press, large book. In the last 2 decades, analytical developments in the computer that have transformed antenna design from an empirical art to an engineering science. The geometric theory of diffraction be credited with a major role in this transformation. GTD, now commonly considered to embrace all procedures involving diffracted rays, has become a sophisticated analysis design tool. So yeah, the diffraction in terms of the resonance of circuits and resonant circuits, as with regards to the oscillator, the resonator, the synchrodyne or homodyne, and the heterodyne, and phase lock loop. Because then everything these days, like, well, all we want is digital signal anyways. We'll just take phase lock loop. And these sorts of accounts, then for diffraction getting involved, diffraction is optical. And so, and above that, in refringence and this kind of thing. So then, relating that geometric theory of diffraction to this is sort of an account of projection. Other IEEE press books, for example, there's electromagnetic horn antennas. Many works here. A volume in the IEEE Press selected reprint series, prepared on the sponsorship of the IEEE Antennas and Propagation Society, by Robert C. Hansen, consulting engineer, Tarzana, California. John Wiley and Sons, 1981. So he's got a bunch of papers. This is a survey. It's like a proceedings. It's got a ton of different papers. I'm going to be looking at this for a while because diffraction is just like, it's just a fraction of differences. And so then getting that all applied to all these things has for like the linear fractional equation and the Claros and D'Alembert's equation, the integral equations, that these are, how one would put it, having that their envelope is the identity dimension. So this geometric theory of diffraction is going to have some relation to that. Geometric diffraction, and then the footnote says this is an appropriate name, but geometric theory of diffraction has become widely used and is used throughout this volume. Geometric diffraction was developed in the 50s by Joe Keller and his colleagues at NYU based on developments in optics by Van Kampen and others. Only a few of these early papers can be included here. These developed the concept of diffracted rays and derived diffraction coefficients for some simple shapes. Multiply diffracted rays in an aperture and a screen are included. The Sommerfeld-Fresnel integral factor is incorporated by Millar, M-I-L-L-A-R. Finally, a useful review of asymptotic solutions, including examples of the Lüneburg-Klein series and GTD with simple shapes such as circular cylinder, is given by Quiyum-Jian. In the references below, the last paper is included, even though it is dated 1974, as it is a review of USSR contributions and references. A bibliography of diffraction papers before 1957 is given by Logan. Talking about Kirchhoff's integral, and then there's Fresnel integral. Kirchhoff's integral is about RLC or resonant circuits, resistance, inductance, and capacitance circuits. Talking about light amplitude is with source. And then what I'm looking for is when he mentions diffractions, because what it's talking about is a method of stationary phase. So that's what happens because electromagnetic radiation is back and forth between light and electricity and current and static current and or static potentials and models of flux and flow and these kinds of things. That they're kind of put together here when it's not so necessarily the way things would be, because of things like the horizon and light going around in its flux and flow with regards to Fresnel integral, and then otherwise these accounts of the radio and like diffraction diagrams and these kinds of things, or the Cook's diagram, the idea of the usual account for antenna design of power and intensity of signal with regards to various technologies of antenna, the radiative transfer of signal and information in the electromagnetic spectrum. The electromagnetic spectrum of radio waves. Talking about the optical ray. So for rays and waves. Anyways, this would be a great book. It reminds me a little bit about the Symposium on Turbulence from about 1969 or 1970. Here is this antenna's diffraction theory. And it'll probably also be about things like stealth and these kinds of things. Empty logic. So this is a bit of a different course. Madhyamika Buddhism from Chinese Sources by Sui Li Cheng. There's been a growing interest in Buddhist thought among Western scholars, especially in the philosophical teachings of the Madhyamika. So the Madhyamika is about the Mahayana Buddhism. It's kind of like a structuralist, a rational kind of account. In this book, Professor Cheng deals with his principal doctrines, his philosophy, and his influence on Zen Buddhism. It is our mind that moves. Madhyamika Buddhism was founded by Nagarjuna in India in the 2nd century AD. It is considered to be the most important outcome of Buddhist teaching and philosophical Buddhism par excellence. Nagarjuna is often regarded as the father of Mahayana Buddhism. Mahayana. Since many of Nagarjuna's Sanskrit writings have disappeared, this book expounds his teaching as presented in the Chinese sources, which predate the later Sanskrit and Tibetan sources commonly referred to. So this was bought in Kathmandu, Pilgrim's Book House, Kathmandu. For 360 rupees. Rupia. Empty logic. Madhyamika Buddhism from Chinese sources. So this here would get related to usual accounts of Hegel and being a nothing. And that is for dual monism and the accounts of since antiquity of these things. Copyright 1984 by Philosophical Library, Inc., New York, New York. First Indian edition, Delhi, 1981. To the memory of Chu Huangfang, 1890 to 1941. General introduction, principal Madhyamika doctrines, Madhyamika and Zen, the Madhyamika treatment of philosophical issues, Nagarjuna, Kant, and Wittgenstein. See, I would give it instead to Nagarjuna, Kant, and Hegel, because Wittgenstein is Wittgenstein is just obstinate. Something to read more thoroughly later and as part of a proper account of that kind of thing. Lawless Universe, Science and the Hunt for Reality by Joe Rosen. Lawless Universe, a new book. Time. Johns Hopkins University Press, Baltimore, 2010. Science and the Hunt for Reality, for Mira. Objective or subjective, that is the question. The science of nature and the nature of science. Theory, explanation, not speculation. Is science the whole story? Science and metaphysics. Transcendence and non-transcendence. Our unique universe. Nature's laws. Facing the universe. The hunt for reality. So that it has metaphysical positions here. He says physics, science and physics, especially since the 20th century, radically changed the conception of nature with regards to the system, but it's just the new system of the world. And he says the public who pays for this should be given the opportunity to share it. Fortunately, a number of scientists who possess the ultra-rare talent of being able to explain their fields to those willing to make the effort to understand have written popularizing books in recent years. Among them are scientists who themselves play active, even pivotal roles in the advancement of modern science. So it's kind of speaking to Lincoln Barnett on Einstein on popular science. From that Logos 2000, popular physics. And then he's going to, this is sort of a philosophical development, so he's going to end up saying what he's talking about. He's talking about there being a theory of everything in a whole and order and laws. Oh, here he says, to the philosophy-minded reader, I should emphasize that this is not a philosophical treatise. It's not, he's saying. It is not. I'm writing about science and its near neighborhood. I try to present relevant issues as a scientist, not as a philosopher. If I use certain terms and concepts loosely by your standards of the philosophical lexicon, I do so to help the presentation clarify the issues. It says, now let's get down to business and see how science operates within a lawless universe, and how science serves us in our quest for an objective understanding of nature. So, the cosmological principle that there are laws in the universe and they're the same everywhere can still held up by, and science is the idea of constantly testing that, constantly examining and testing that. So, yeah, it's not a lawless universe, it's just looking for any violations of the law. The nature of the reality has been the subject of extensive, deeply searching philosophical thought, discussion, and argument throughout the ages. In our own age, the issue is still far from resolved and arouses undiminished fervor. So, metaphysical positions. Talks about metaphysical position of realism, presented in Realism and Idealism, chapter 6. There, realism was presented as a position that the order and laws of nature are inherent to the world we observe and are independent observers. I opposed realism to idealism. See, here they're put together. There's a contradistinction, none, that it is the idealism that's the realism, in which the order and laws of nature exist wholly in the mind of the observer. You see that here that there's strong mathematical Platonism is like they're wholly outside the mind of the observer. And everybody has the same window to the perfect circle in the straight line. I then proposed a hybrid position that nature does possess objective order, whereas laws are a human device. That speaks to things like Bohm and the implicate order, and then the laws of our theories of our science is a perfectly correct interpretation of the theory of science. That the theory is whatever rules that there are to be put together that offer explanatory power and predictive power within the theory and are not falsified or invalidated by the data or experiment. Also the design of experiment and as about the energy and configuration experiment. Realism claims that there is a real world out there. And that pervades the presentation in this book simply because my own worldview is basically realist, as is that of almost all scientists. Realism in this sense is usually placed as in opposition to positivism, which is the metaphysical position that only our sense data are fundamental, are fundamental. Realists and positivists both agree that our measurements and observations are the source of our scientific knowledge of nature. And he gives some differences between realists and positivists, or reductionists and anti-reductionists. That reductionism into nominalism and logicism or positivism is kind of the opposite of realism and objectivism and anti-reductionism. So this is a pretty good account of this is the language talking about the theory of science. And here we'd point to something like Bernard d'Espagnat's great work, and it was read here quite thoroughly. A few minutes left today. Cosmological Constants, Papers in Modern Cosmology, edited by Jeremy Bernstein and Gerald Feinberg. Where I'm reading it here, it's about Hubble. It's a paper from Hubble, a relation between distance and radial velocity. So this is kind of like for Hubble rotation, this is kind of a thing. And what this book is Cosmological Constants gathers in one place the seminal works of such greats as Einstein, Hubble, Sakharov, Weinberg, and Friedman, much of which is hard to find or unavailable in English. And the editors provide a series of introductions that describe the contributions of papers and tie them together, making these classics more accessible to students of physics and astronomy. I'll be looking at this for a while. 1986. Columbia University Press. To the memory of our teachers Philip Frank and Ernest Nagel. So Nagel will show up a lot. Nagel and Newman. So it has a bunch of papers. And if you want to study astronomy, there's the ADSABS service is out of Harvard. It's called ADSABS, ADS-ABS, and it's a website, and they have astronomy articles since forever. So that's 59th Annual Meeting Papers, the Symposium on Ion Exchange and Chromatography in Analytical Chemistry. So this is more the applied, from the ASTM Special Technical Publications, number 195, published by the American Society for Testing Materials, so metrology and the like. Ugh. From the Biotechnics Laboratories, the Symposium on Ion Exchange and Chromatography in Analytical Chemistry. Solution of participants, ion exchange resins, adsorption of negatively charged complexes. So these kinds of things you can design resin matrices. You don't need nanomaterials to make various notions of osmotic membranes and the like. Geometric Quantization, second edition, NMJ Woodhouse, Woodhousc. Oxford Mathematical Monographs, Oxford Science Publications. $42. Clarendon Press, Oxford. Among the Oxford Mathematical Monographs, geometric quantization continues to be a popular research topic. So geometric quantization is, as of other matters, quantization is like how do you make for a discrete element within a continuum of things? How do you individuate an element? And then making that quantized so that it can be a quantity, so it adds back up. So how do you make it so that the measure of it is established? So mensuration and quantization is after the quantization is denormalization, saying, hey, we're somehow breaking a chunk out of this thing to call it a part of this thing. That's what quantization is. And it's talking about the Copenhagen philosophy, so that would be of quantum theory. According to Copenhagen philosophy, the physical predictions of a quantum theory must be formulated in terms of classical concepts. So that, with regards to determinism and non-determinism, is about kind of as to whether it includes adding the non-determinism to classical concepts. And so the Copenhagen interpretation, saying that is so, I guess that's sort of a strong account, but it's still built, and all the classical concepts by then include the potentialistic accounts of Lagrange. And so it's for Copenhagen and Solvay and saying, well, this is all quantum mechanics is or ever will be. It has then the assumptions that go into that build why that's so. Kind of automatically get broken right at the root as soon as it comes around. So that said, that's for an account of why quantization is denormalization. And then the renormalizing and the renormalizable is like, well, after we got after that hump, and then another hump that shakes everything loose, and we're trying to keep it put together. Then another one, then it's renormalizable, and now we forget it ever happened. And so it's hypocritical to make an account that something's renormalizable unless it gets to how it was denormalized to get there. Did snow a bit today, but it's not really staying here in the valleys. It's up in the uplands a bit. Still quite a deficit. Thus, in addition to the traditional structure of Hilbert space, so Hilbert space is like in the complex analytic. It's, as of F, the diagram of the complex numbers and R squared. Has all the many issues involved with that too. More than will be addressed here in a talk like this, but are part of the ongoing discussions in my 10,000s essays written to Usenet. So the particular question that geometric quantization attempts to answer is, to what extent is canonical quantization a well-defined mathematical procedure, and To what extent does it depend on the choice of canonical coordinates? So that's great. And saying that it's to make for a geometrical account is for things like saying is like, you know, the long-range program might say it's making a great algebra of things, but algebraic geometry is geometrical here. We're geometers here. The world measure, if we're going to be solving the measure problem, we're going to be using the world measure of these things, vis-a-vis the Buckingham pi naturally simplified terms. That not being classical anymore. Starting with the classical phase space, so the configuration space and the phase space, represented by a symplectic manifold, so continuous and furthermore freely analytic, that is given, that it's not broken anywhere. One looks for a geometric coordinate-free construction for the Hilbert space and observables of the underlying quantum theory with no explicit dependence on a particular coordinate system. Such construction can be expected to give a very clear insight into the ambiguities involved in passing from the classical to the quantum domain, or the super-classicism. So here, instead of retro-finitism, there's super-classicism. And that the continuum mechanics is what quantum mechanics really is. So there's much to be read of this, and but it's kind of trying to make up formalisms to address the deficiencies of the perceived obvious paradoxes in usual accounts of the standard accounts of the non-standard, as they would be. Parallel transport, Fock-Hartree, Bohr-Sommerfeld. See, for example, Wells, Weismann, Vaisman, or Griffiths and Harris, in 1978. Well, gentle readers, that's reading foundations for today.